on the west side, but we'll get to that. The salt pan here, though, it's covered in salt, and that salt forms because the valley floor floods sometimes. It's flooded with water. The water gets down onto the salt pan, and as it's moving down onto the salt pan, it picks up more salt, and then as it evaporates, it leaves behind salt. This particular, I just took this picture last year, and it's from the Hurricane Hillary that kind of affected the whole place about 2 years ago. This picture is taken in 2005, though, so it does happen. But it does happen every so often. The salt pan floods, and one of the main sources of water is the Amargosa River, which starts up here near Beatty, Nevada, and it flows south through these towns of Shoshone and Tecopa, and comes back and empties out into Death Valley. Now, the Amargosa River is dry for most of its length for most of the year, but when there's a lot of rain, you'll see surface water flowing along in the Amargosa River, and it ends up in Death Valley, and then that's the end. There's no outlet to Death Valley. Eventually, it evaporates and it leaves behind salt. So you can go down there after when it's evaporating, and you can see the salt crystallization going on. And eventually it firms up, and you can see these beautiful fractures in the salt pan. As it's drying and shrinking, you get cracks, and then you've got water coming up between the cracks, and it carries salt with it, and it precipitates it as these ridges at the surface. And this here is a drill core that was done in the 1990s. They went down to about 600 feet. This is in meters, so down to 180 meters or a little deeper. And what they found was evidence for a lake that existed between 10 and 35,000 years ago that was a permanent lake in Death Valley, and one that existed between 120 and extensive, certainly a lot longer lived. And these lake climate was a lot wetter, and you can see evidence for this older one of them. There's this gravel ridge, and the road goes right through it. And this ridge extends probably a spit coming off of this hill in the foreground. But what's really cool is if you go down onto the road and you look into Death Valley, you can see here's the spit, the gravel that was deposited along near the edge of this lake, and you can look into Death Valley, and it was full of water up to this point, all the way, even actually about a mile past this ridge was the actual high stand of the lake. So you can just look at this photo and just see how much water used to occupy Death Valley at its maximum. You can see at shoreline, what's called Shoreline Butte, you can see these horizontal lines. These are old strand lines from the lake. They get up to an elevation of 200, 250 feet above sea level. So because the valley floor is almost 300 feet below sea level, this lake was over 500 feet deep. And if you go back to Badwater, you can see these old deposits here lining the edge of the mountains. And these are gravel deposits cemented together with the material called tufa. It's a spring deposit that you often see in these saline lakes. And it's really quite remote. It's one of my favorites, called the Ibex Dunes. And if you look at this map, it shows the national park outlined in green, and these orange spots, these are the sand dunes in Death Valley. So there's 5 different dune fields, and then there's a couple outside the park, Big Dune and Dumont Dunes down here. We think about sand dunes as sort of the quintessential desert landform, and we think of deserts as often being very sandy. And look how much area is occupied by sand. Not very much. You could use Google Earth. You can estimate the area of these dunes collectively total about 13.6 square miles, but Death Valley is an area of 5,270 square miles. So this is less than 0.25% of the area of Death Valley is covered by sand dunes. So a really tiny fraction. But still, they're pretty amazing. And this one here, the Mesquite Flat Dunes, are very accessible. This is Stovepipe Wells, one of the places you might stay if you visit Death Valley. This is Furnace Place to avoid. But Stovepipe Wells here is it's a little nicer. It's right next to the dunes, and you can walk out onto them. And the Mesquite Flat Dunes look like this from the air. And you can, this beautiful backdrop here, the funeral range. But you can see there's a couple different shape, and then these other ones down here. These are called star dunes, which have 3 or more arms to them. But if you look at these ones, these are the transverse dunes, and they form perpendicular to the prevailing wind direction. So the sand blows up the gentle side of the dune and then kind of cascades down the steeper lee side. These star dunes, however, they indicate wind is kind of going all over the place. And so you can see that it's not just a straightforward picture of the prevailing wind direction. And if you look at dunes, and you can see that the prevailing wind directions can shift quite a lot at different times of the year, or even in a single day. So you can expect to see star dunes. And in fact, in most of these other dune fields, you can also see those star dunes with 3 or more arms going off in different directions. Another dune areas, which are these kind of hard-packed, very fine sediment deposited in standing water. They're like old lake beds. And I used to puzzle over these quite a lot, thinking, wow, maybe they're remnants of Glacial Lake Manly. That was the Ice Age era lake that filled Death Valley. But you can quickly disabuse yourself of that notion when you see these lake beds, and you can see that they're sitting on top of sand and they're below sand. So these basically form with the sand dunes. And with Hiller 2 years ago, during the flooding that took place then, the sand dunes got flooded, and there were standing bodies of water out in the dunes. And you can see how that happens. Again, here, this is a Google Maps images. There's this big alluvial fan here coming out of this canyon. And here are the dunes right here. And just to zoom in a little bit, well, here's the parking lot. You can walk right out. But you can see that there's like a direct path from these channels on the fan right into the dunes. And these white areas, these are the lake bed deposits. I'm not sure you'd call them lakes, but they're very fine deposits deposited in standing water. And here's another, these are the Eureka Dunes, which are the tallest dunes in California. They get up over 600 feet high. We still had a long way to go and never made it. A crater called Ubehebe Crater. It's about 2,100 years old. It's 500 feet deep. It's about a half a mile across. And it formed when rising basaltic magma intersected the groundwater and caused a major explosion and just kind of blew everything out. And so you can see deposits from that explosion up here, these gray stratified deposits, suggesting that during this eruption, the explosiveness of the eruption probably it pulsated some. So you got sort of different grain sizes here, and they're sitting on top of older alluvial fan deposits underneath. But it's not just Ubehebe Crater. You can go up and you can see it's part of a whole field of craters. And here's main Ubehebe Crater, and then here's some other ones right here. And then here's called Little Hebe Crater is kind of in the middle of those 3. You'll notice there's little playa deposits here when there's standing water. But if you look at the Little Hebe Crater, you can, there's also a trail you can walk around and take a look, just walk around the rims of these things. It's very cool. But if you look at Little Hebe Crater itself, not only is it picturesque, but you can zoom in on this material. These are the deposits from the main Ubehebe eruption, and they're sitting on deposits from Little Hebe Crater. So we've got these 2 different materials, but in between, we've got the Ubehebe. that suggests that when the main Ube-Hebe products landed on the little Hebe products, so that what people think now is that the short period of time, days to weeks. So just kind of a whole, it must have been an amazing time, but formed and probably formed over a very short period of time. And I see another volcanic feature called Cinder Hill. And you can see that it's actually split here, and it's split by a fault zone. If you, you can drive down this road and go right to it. It's a well-graded dirt road, but the highway is right here. So if you look at it from the highway, it looks something like this. And the two pieces of this cinder cone are offset by 699 feet. It's measured very exactly. And if you go down there and look at it, you can see the material that makes up the old cone, and you can see where the fault goes, and you can look up into Death Valley itself. Now, we're not entirely sure when this cinder cone formed. Deposits, which are between about 26,000 and 6,000 years old. It has to be younger than the Lake Manly deposits. There's a place you can see it sitting 26,000 years old. So you can do the math, and the estimate then for the amount, the rate at which this thing has been offset is changed. But by then looking at what other faults people have figured out with other faults and so on, folks tend to agree that it's somewhere between 1 and 8 millimeters a year. Now, 8 millimeters a year is still really fast. If you think about it, if this fault moved, if it's had a slip event, say every 1,000 years, translate to a really big earthquake. And this is on a major fault. It's on what's called the Southern Death Valley Fault Zone. This is looking to the southeast along the fault. Here's Crater Hill, right, or Cinder Hill right here. And so it's right along that fault. Now, if you start seeing how this might fit in with the whole scheme, and this leads into how Death Valley itself actually formed. So the next slide and over here we've got the Black Mountains on the right and the Panamint Mountains. You'll notice that the Panamint Mountains are not as steep, but the Black Mountains are. So there's a real asymmetry there. And it's because the Black Mountains have been uplifted along this big fault zone. And the movement on that fault zone is up and down the fault plane. It's called a normal fault. Whereas this fault here on the cinder cone to the ground surface. And they're related. And they're related. If you look at the next slide, we'll show a map. And here is the Southern Death Valley Fault Zone down here. And you'll see that the Southern Death Valley Fault Zone steps up onto the Northern Death Valley Fault Zone. And here's an aerial shot of the Northern Death Valley Fault Zone. And if you look at this, the upper part of the Northern Death Valley Fault Zone is moving to the right. This block down here is moving up to the northwest. The fault zone here is moving to the southeast. So that's pulling this area apart. And so the Black Mountains, that is forming pretty much in response to this fault moving up here and moving Death Valley Fault. And here's the Landsat image, whole picture, and we'll kind of talk about what we can see there. We got the Panamint Mountains on the left, the Black Mountains on the right. You can see how abrupt there's no transition at all. You're driving along the road. You actually, when you go around these alluvial fans, you actually have to turn the wheel of the car to avoid hitting a mountain. It's the only place I know where you actually have to do that. And it's so abrupt, and it'll be active in the future fault zone. Whereas the Panamint Mountains, the fault that they ride into the valley floor, and so the active faulting is not over here. It's just eroding, and it gets in a very wide cross section might look something like this. Where here you've got the normal fault along the front of the Black Mountains. Everything's tilting back to the east, lifts those up, and those tilt down to the east. And that tilting is why these alluvial fans can spread out so much. They can basically the tilt. Now the valley floor itself is tilted very, very slightly. It still has that same effect. And the alluvial fans on this side of the range, they get trapped, so they don't spread out at all. And the same thing with the salt pan. It tends to get crowded up into that fault. And we can see that this has to be crustal extension. The crust is actually used to match up, right? But down the fault surface. So this is a manifestation of crustal extension that has caused the range to rise. In the crest of the range, you can see just again how steep the front of the Black Mountains are. So this photo would coincide with here. And then this side, they're tilted back to the east, would coincide with right here. you can see more mountain ranges that are pretty much the same story. The ranges have come up along a fault zone and they tilt, and then the valley floor is in between them. This is the Spring Mountains here. On the other side is Las Vegas Valley. From the air, you can act these alternating ranges and basins and ranges and basins. It's called the Basin and Range Province in the United States. And the colors they represent the different rock types. So those are the mountains, whereas the white areas are the alluvial or the gravel-filled valleys in between here. But all across Nevada, all the way to province. And it's all pretty much this, where you've got a fault zone causing the valley floor to drop and the range to rise and tilt back into the next valley. And it's all crustal extension. And in Death Valley, this extension is. If you go back to Badwater, you can see this band where the fault has broken through the gravel, then the gravel that's right there. So it has to be really pretty at all the time. It's interesting also, the spring here at Badwater is right on the trace of the fault area, which is just to the north. This is still the Black here. And you can see these features called wineglass canyons. And so this would be the bowl of the canyon. If you think about canyons through time, they erode, they get wider, they get a little gentler, their gradient gets gentler. You would expect that up at the stem, and that's because it's repeatedly getting uplifted along the fault and into the canyon. So these wineglass canyons along the fault. Here's one looking straight down at a wineglass canyon. Here's the bowl, and here's the stem, and then this alluvial fan down here. Is I was working with a grad student on his master's thesis down there. When I took this picture, we were way up. We're 8,000 feet above the valley floor, tilted the plane, and there I was staring straight down at this thing. I'm glad I took a picture. Hard to see, but there's a step. This is a place called Natural Bridge Canyon. You know, the canyon and the walls are made out of older time a little bit. And if you look at all the bedrock in this photo, it's all volcanic rock. And deep in the canyon over here, we've got metamorphic rock. Everything else is volcanic. So you would think volcanic particles being transported down the canyon and some metamorphic ones. Just about all volcanic particles, but there were 2 of them. But there's a bunch you can see as you walk up the canyon. But the walls contain only volcanic particles. So and you poke around looking at all the grouting, but volcanic material. And so what that's telling us is that when these deposits were formed, this was all covered up by the volcanic material, fan deposits, and it can tell us something about the history of the range. And if you go up to the sort of main Furnace Creek area, you can see these rocks. It's actually called the Furnace Creek Formation. And these are more than years old. And you can see they're tilted. So angle, maybe up to 3 degrees on an alluvial fan, but now they're tilted at like 45 degrees here. So there's been a lot of activity since they formed, but also these are these older alluvial fan deposits telling us that there were mountains when they were being deposited. You can see they get rocks in there too, but and if you go to this place called Zabriskie Point, you find finer grain down here, and we've got mostly playa and river deposits right here. And they interfinger. And in fact, you can see that at this place where we've got lake deposits here, just kind of blending into alluvial fan deposits. And that's just what we see in Death Valley, right? We've got alluvial fans coming down off the mountains, and then there's this big playa that sometimes is filled with a lake. And so called the Furnace Creek Basin, which was sort of like an old Death Valley that existed between 6 and 3 million years ago. And it had, mountains there forming alluvial fans. And there was this, sometimes it was dry, sometimes it was wet. And then it got dammed and it became a lake. And that was all taking place until about 3 million years ago. The fault system became active and started then uplifting those old deposits in the front of the form about 3 million stuff. And if you look at a geologic map of really long and involved history, over on the right is a geologic time scale showing the major divisions of Earth history, Precambrian, Paleozoic, Mesozoic, Cenozoic, where you start to see shelly fossils in the rock record. You have Mesozoic, the time of dinosaurs, Cenozoic, time of mammals. And we in the upper part of the Cenozoic, dominated by crustal extension. But you'll see that the bedrock of Death Valley is much, much older. And what I want to do for just this last part of the talk is skip through some of these features to show you just how extensive this history is. And are all Paleozoic or the very upper part of the Precambrian. And during that time, it was a shallow ocean, and all those sedimentary rocks, I'll talk about that a little bit, was another period of mountain building. It wasn't crustal extension like we have today, but it was crustal compression. And then after that, And a lot of these rocks also are igneous rocks like granite that intruded the crust. And then go back, whoops, sorry, and briefly talk a little bit about the Precambrian colors. So the Paleozoic rocks, we can see those exposed in a number of places. You see a lot of limestone and dolomite, which by themselves are indicative of generally indicative of a shallow marine environment. You can see that then in the Amargosa Valley. These are very tilted dolomite. In the Panamint Mountains, you can see these Paleozoic rocks, and they're all tilted, just like a tilted fault block should be, into Death Valley. And besides the rock types and the basic features that you can see in the rocks, you can also see fossils that were marine fossils. These are trilobites and what's called the Wood Canyon Formation. So these are, generally speaking, throughout most of the Paleozoic, a shallow marine environment. And we can see those rocks, we can measure their thicknesses. Because they're tilted, so you can walk along a ridge line and actually measure the thickness of the beds. And they total up to be over 20,000 feet of sedimentary rock. And you can just imagine how long it took to accumulate all that sediment. But that 20,000 feet of rock was then deformed during this compressional mountain building event in the Mesozoic. And one of the expressions of compressional mountain building is to form folds. And you can see this giant fold here that's formed because of crustal compression. You can drive down this canyon. This is called Titus Canyon. Not only are there folds from the crustal compression, but there are thrust faults that put older rock up over younger rock. And if you go to this place called the Racetrack, you can see intrusive igneous rocks. Now, if you're not familiar with what these are an igneous rock. Any igneous rock is one that forms cools and crystallizes from a liquid state. So a volcanic rock is igneous, but that's one that cools down at the Earth's surface. If it cools down below the Earth's surface, like a granite would, it would be an intrusive igneous rock. And you can see you have all these intrusive igneous rocks up around the Racetrack. So you can see those up here, but these rocks that have skated across the Playa surface have been a mystery for a long time. We think now we know how they actually slide, but there are all sorts of ideas of how you can get. Some of these rocks are big. I think it was 2012, they were caught on video sliding. And the story is that, well, this fold in the winter, and if it's wet, it'll freeze over at night, and you'll get a thin sheet of ice over the Playa surface. And then in the morning, when the sun comes out, the ice starts breaking up, and you can have these big sheets of ice. Just a gentle wind can blow the ice, and as the ice moves, it can push the rocks. And that's what was caught on video. Oh yeah, wow. You'll have to tell me where you saw that, because I just read about it. Okay. But anyway, back to the bedrock. Folded Paleozoic rock formed during the Mesozoic. This intrusive igneous rock. Take a simplified cross-section of the area, where here's the granitic rock intruding everything, Paleozoic rock and thrust faulted Paleozoic rock. 20,000 feet of that rock deposited crustal compression in the intrusion material that's all related to crustal extension. And C has a lot of features in it. Only for the Pahrump group is the Kingston Peak Formation. You can find a lot of these fine-grained marine sediments, kind of like what these have been interpreted as. So you get glacial deposits of different grain sizes, and then they got remote. But they also have these things where these big boulders are rock. Now the grain size of a sedimentary rock is in the system. So if you have fast-moving water, you can get pretty coarse, get washed out of there. So in lakes or deep ocean environments, you get boulder stuck in the middle of all that. And with boulders were transported out bergs. And then as the iceberg melted, I've seen this on a sample, but actually of glacial striations on them. So in this period of time in the later part of the Precambrian were in equatorial time. It's called just about the whole planet was Hurum group and ended up with the supercontinent of Rodinia. But yeah, so it goes with basement rock that's preserving something here that's going on as well. So we've got an amazing the Cenozoic, a period of mountain building. We can see that going on today. We see evidence of a Mesozoic along with these big bodies of these intrusive bodies with probably this compressional mountain building over 20,000 feet of rock. Before that, you have, the Pahrump group recording snowball earth, and Rodinia was originated as a sediment, as a sedimentary rock. So it goes back. So, I mean, I haven't really referred at all to radium. Looking at tens of thousands of years, or certainly kind of an incomprehensible length of time. These are just from one geologic era to the next. The mountain building in Death Valley today, Mesozoic boundary was at about 66, Paleozoic to Mesozoic about 252 million years ago. End of the Precambrian was at 538, and that basement rock of 1.7 billion years old. But it goes close with just a little passage that I got out of one of my favorite readings when I was in college, where it's from Don Eicher in his historical geology book, where he takes account, compresses all of Earth history into a single year. And I modified it slightly, but the first evidence of life would appear near the end of March. The first animals that formed shelly followed November 17th. Land plants such as moss appeared November 23rd, followed by the first land animals. Dinosaurs wandered next. Death Valley started opening about 6:15 p.m. on December 31st, and the Ice Age ruled the Western world for 3 seconds, from 11:59:44 until 11:59:47, and death before midnight. Thank you.
Does anybody have any questions for Dr. Miller? You watch your eyes, they can be a little bright. Just raise your hand and I can bring you the microphone.
There's a question. Oh, I guess she's bringing the microphone.
I have two questions and they're related.
Okay.
Both related to how deep was the water when there was water there? And the second related to that is, are there turbidites?
Are there turbidites? Okay. So when you say, are you saying when it was a shallow ocean?
I mean, I'm talking the geological record.
Okay. So for Glacial Lake Manly, it got to a depth of more than 5. Lake Hillary, which is what I like to call it, but they still call it Lake Manly, from just last year, got to a depth of, a couple feet at the most. If you look at the rock record, it's by and large shallow marine. That is no deeper than about 100 meters, because those the carbonate rocks require a thriving ecology to precipitate low enough that there's light penetration for photosynthesis. So for the most part, the shallow marine environment throughout much of the Paleozoic was pretty shallow. Although there were times when it was deeper, and you can see turbidites, I believe, in like the Bird Spring Formation and some of these other ones that are kind of on the western side of Death Valley as you get farther off the shelf. And so there are turbidites in some of the Paleozoic rocks, and in some of the, certainly those pictures of the Kingston Peak Formation, those red rocks at the end, there are turbidites in there. And turbidites, for those of you who don't know, thank you. They're deposits of these turbid flow down off on a steeper gradient off the sediment flowing down underneath the water. And they tend to form beds that are coarser grained at the bottom and finer up at the top, coarse to fine, these sort of repeated beds. So there's some turbidites out there. We've got turbidites all over the place in Oregon. It's great. Anyway.
Any other questions?
Overwhelming to go there. There's rock everywhere. It's great. You don't have to look at the plants. Sorry, I want to make a snarky kid from the rocks. Scotty's Castle.
My father named Scott, and he took me to Scotty. He said, "Oh, they got a tower." But is that where the place where you said is all the visitors?
Oh, no, the visitors center, and they have an 18-hole golf course. Yeah. And it can be kind of overwhelming. There's this onslaught of humans. But they've got a really nice visitor center there. But Scotty's Castle, which was I think in like the 1920s or 30s, there's this guy named Scotty who was a real shyster, and he talked this guy in Illinois, I think, insurance guy who had a lot of money. They became friends, and he talked him into building this big home in the desert. And oh,
We got a question that are back.
oh, okay.
Hold on 1 second. Go ahead.
I was just going to ask, what is your favorite thing about Death Valley, and what has been the most surprising thing to you? Because I know it's been a
favorite
long.
thing about Death Valley and most surprising. I think my favorite thing is if I've been out hiking during the day or trying to understand back to my car, and it's flowing and it's calm and it's stunning. It's really beautiful. I think that's my favorite thing about it. And that can be just about anywhere. I think what I found most surprising, and I didn't even talk about it tonight, was how interested I got in the whole pupfish story, because of fish called pupfish. They're about this big, and they live in these isolated environments around Death Valley, and each of them is a different species. And they're limited to an area. Its whole habitat is about as big as the stage, and it goes down a couple feet. And that's its whole 100 degrees. And its population really plummeted, but then it's back up, and people are really excited about how many individuals there are now, and they counted over 200. So they seem to be doing okay right now, but they've had quite the, in the last, they were the first test of the endangered species going down. And so they were able to stop that and preserve the fish. And it's quite.
Follow up, aside from the fish, are you doing any active research down there right now, and can you share what it might be?
Yes, I have a student who's finishing up her project right now. I could show you on, let's see if I can swing through this.
If you guys could also do me a favor, just raise your hand for a question, and then I can come to you. So
when I get to a map, oh gosh, she's been working in the southern part of the Black Mountains, which is where I've done most of my research. Just about all my research. Well, not quite. Most of it is, but she's working right down in here in an area called the Amargosa Chaos. And it's named that because it's truly chaotic. The faulting is just ridiculous. It's so faulted, and it's people have been, they'll say going on there, and so it fits in with anybody's idea for what's happening, the faulting and the evolution of the faults, and in overall directionality to the movement. So yeah, sorry,
we have people back there.
yeah,
So if you could just hold your hand up,
but yeah, sorry.
Hold on 1 second. How low?
Minus 282 feet below sea level.
Okay, I'm hurrying. Hold on.
National Park Service decided to hire you as a tour.
Yes.
Well, thank you for them. Actually, I got a great story. I was volunteering for them in the visitor center, and in exchange for volunteering, they'll put me up for a few nights, and so I can that it said a little sign said "Ask a Geologist." So I was there. I had a geologic map and a bunch of rocks, and I'd have sometimes people come up. They're a lot of fun, and we're all into looking at the rocks. This one guy come up, and he looked at me and he goes, "I'll bet you know where the bathroom is." And I said, "Yep." Anyway, that's my best story about that. Yeah, in the visitor center. Gotta follow the signs.
One of the things that really struck me was when you showed that basement rock, how layers what is the timing, Ollie? Were those basement rock layerings in a water?
The basement rock has that layering to it. It's not a sedimentary layering. It's layering called foliation. And then you take some pre-existing rock, it's at a high temperature and has a directed pressure on it, and it comes mineral grains to recrystalline minerals. But because of the directed pressure, those minerals form in a preferred orientation. And so that gives them the layering, which is the metamorphic rocks that originated from a sedimentary rock. Those might have indicated 7 billion years ago, but certainly the overlying sedimentary rocks in the Pahrump group have a lot of marine origin.
It's more about economics. Has there been an attempt to mine Death Valley?
The minerals like silver and copper, partly because of the very different things like that, and the conditions are really difficult. There are a couple mines that are also a lot of scams in the history. The minerals that were the most economic borate deposits in the 1920s, Death Valley was of borates in the world. And then but for a while, Death Valley, there's evidence for what they did down on the playa and things like that. And there are a lot of talc deposits that are in the lower part of the Pahrump group. It became a national monument in the 1930s, and then a national park in I think 1994. Still some mining going on inside, but it's been anything new. Huh? Good question.
With our unfortunate, we did actually post the whole video on there again. So anybody that missed the beginning, if you have anybody that knows that, does anybody have any other questions? None. It's still up and running. So thank you. We have several of our awesome, if you have any questions, all the awesome student research that was going on earlier, I was talking about. These are the great Derek Morelli back here with chemistry, Erin Coiner, physics and engineering. Wynn is back there. Yes, she's there. And then we have Amy Burgess. And Nick is back there as well somewhere. There we go. Yes, and I actually was leaving him to the end. I wanted to mention the geology lecture series, so we're just grateful that began, and we kind of just ran with it. So thank you all for being here lecture, and please back here to kind of just keep track of how many people show up to these types of events so that we can keep providing those. Dr. Miller has books back there as well. And if you didn't get a chance to see, I have a display of a bunch of, check that out. There's also some information for. Thank you again.